Today we're going to talk about heating the atmosphere and the difference between heat and temperature. Our objectives for the day is to be able to differentiate between heat and temperature, describe the three mechanisms of heat transfer, explain whether dark objects or light objects will be better radiators of heat, and describe the greenhouse effect. The concepts of heat and temperature are often confused. The phrase "in the heat of the day" is one common expression in which the word heat is misused to describe the concept of temperature. Heat is the energy transferred from one object to another because of a difference in temperature, while temperature is the measure of the average kinetic energy of the individual atoms of molecules in a substance. So our temperature, all objects are composed of matter, and inside all matter is atoms, and our atoms move around and they bump into one another and whatever. So our temperature is the kinetic energy, or how fast these molecules are moving, how often they're bumping into each other, whereas our heat is energy transferred or moving between two objects. There's three ways that we transfer this heat. Transfer here is our keyword. Underline that. So our heat is always energy that is transferred, and it results in the changing of the temperature. So to go from this cold object to this hot object, we would have to add some energy or add some heat by putting it on a stove. To cool down this hot object into the cooler object, or change the temperature, we're going to remove heat energy, or heat will be lost into the surrounding environment. There's three different mechanisms of heat transfer. We have conduction, convection, and radiation. It's likely that you remember these three mechanisms from previously in science. We're going to jump into them today briefly, except for we're going to spend a lot of time on radiation. So our conduction is transfer of heat energy through matter by molecules. So our molecules have to be touching. This lady holding a coffee, her hands are touching the cup, which is touching the coffee. So the molecules are transferring that heat energy, and it always transfers from hot to cold. So as we touch this cup, our hands are warming up. Our energy is transferring from hot to cold. If you think about taking food out of the fridge and leaving it on the counter, our cold air is not actually disappearing. The heat from the counter is being transferred into our food to warm it up. So it's transferred from hot to cold. Our second type is convection. Convection, we've heard of convection currents when we were studying plate tectonics. Convection is the transfer of heat by a mass movement or circulation within the object. So our particles here are getting heated up by this stove, and our warmer water rises because it's less dense. Our molecules spread out because they're hot. They don't want to be next to each other. And then this cooler water up top is cooling down because it's further away from the heat source. And that cold material will sink down because it comes more dense. There's molecules squished together because they want to get warmed up. And our last type that we're going to spend the most time talking about today is radiation. Radiation is how the sun heats the earth. It transfers heat in all directions. So although we have it coming down here, the squiggly lines represent all directions. So it'd be scattered all out. It's the only type of energy that can travel through space. So if we look back here, our conduction has to be matter to matter, and our convection doesn't work through large amounts of space. Although we do get convection currents with air, we still have to have some type of material to travel through, and this can travel through empty space. It works in our atmosphere. There's 4 laws that govern radiation. So all objects emit radiant energy, both hot and cold. So our ice is emitting radiant energy or cold waves off the ice, while our 2 penguins here are emitting heat energy in all directions off of them. Nextly, hotter objects radiate more energy per total unit area than colder objects. So in this picture here, we've got a lizard and a guy's hand. So because humans are warm-blooded, we radiate more energy per total unit area, if this represents energy over here, than this little lizard would, because he's a cold-blooded object, so we're emitting more energy than it does. 3. Hottest radiating objects produce the shortest wavelengths. So in the electromagnetic spectrum, which is what this is, we have our wavelengths. It's likely you've seen this somewhere before. Different things produce different wavelengths. Our ultraviolet light right here, which is a lot what we get from the sun, has a shorter wavelength than radio waves, microwaves, infrared waves, which is what bees see in. So the hotter our object is radiated, the more squished or shorter our wavelength would be. As we move up this scale in the electromagnetic spectrum, our shorter wavelengths are also more damaging. And lastly, objects that are good absorbers of radiation are also good emitters. So gases are selective absorbers and radiators. The atmosphere does not absorb certain wavelengths of radiation, but it's a good absorber of others. If we look at this picture, we all know that if you wear a black shirt in the summertime, you're going to get super hot. Whereas if you wear a white shirt, you're going to stay cooler. So our black is going to absorb heat really well, which means that it also emits heat really well. I don't know if you guys have heard of that wives' tale, or that you can fry an egg on the sidewalk. It would work better to fry an egg on a really hot summer's day on the blacktop, because our black is going to emit heat better than the white would. All right, we're going to talk about what happens to solar radiation as it's coming down to Earth. So 5% of our solar radiation is going to get backscattered into space by the atmosphere. So some gases and waters in the atmosphere don't absorb the solar radiation. Instead, they reflect it, so it's transmitted back into back into space. 30% of our solar radiation is lost due to reflection and scattering. I did want to talk briefly about these two words, reflection and scattering. So in reflection, our wavelength is going to hit some sort of molecule. It hits a molecule with X intensity, and it bounces right off that molecule with the same intensity. Whereas in scattering, our radiation hits the molecule and it bounces off in all directions with less intensity. So it scatters the light, or scatters the wavelengths in all different directions with just a little bit less intensity for all of them. %, of our solar radiation is going to be reflected from the clouds. Again, water vapor and other gases reflect that light off the clouds. 20% is absorbed by the clouds. 5% of our solar energy is reflected off the surface of land or sea. And 50% of our solar radiation is actually absorbed by Earth. The atmosphere efficiently absorbs the longer wavelengths emitted by Earth. Water vapor and carbon dioxide are the major absorbing gases that we see in these clouds and up in this atmosphere. When gas molecules absorb these waves, the energy is transformed into motion inside the molecules, which we can see as a rise of temperature. So as our clouds and our atmosphere is absorbing some of this radiation, the temperature increases. So we've got our heat increasing temperature. Gases in the atmosphere will then eventually radiate some of this energy away. Some of it goes up to the sky, where it can be reabsorbed, and the rest is going to be traveled down to Earth, where it will eventually warm our surface. Without the gases that are in the atmosphere, Earth would not be a suitable habitat for living things. As it's absorbing this heat from the solar radiation and sending it down, and it's getting trapped back up, keeps bouncing back up in here, and this is what we call the greenhouse effect. The greenhouse effect helps us keep our planet at a constant temperature. There's a balance of energy transfer into and out of Earth's atmosphere. Over time, the incoming solar radiation is absorbed, reflected, re-radiated. As a result, our average temperature tends to remain constant from year to year. We don't see giant fluctuations. Here we can see the greenhouse effect again. We've got sun, incoming energy. Some of it is lost. The earth absorbs about 50% of it. Air molecules absorb, say, 20-45%-ish. So that's going to get re-radiated between our ozone layer here. We learned about the ozone. Between our ozone layer to keep Earth at a constant temperature. Just want to go back and retouch on our objectives. Today we've differentiated between heat and temperature. We've described the three mechanisms of heat transfer. Through this lesson, you should be able to explain whether dark objects or light objects are going to be better radiators and emitters and absorbers of heat. And we should be able to describe how solar radiation and the greenhouse effect happens.